Welcome back. This is example 2. We are going to evaluate the output y of t given the x of t is a causal signal and we have now zero initial condition. So this system is exactly the same as example 1, only with the difference that now the initial condition is 0. So x of t is again the cosine multiplied by unit step, meaning that it is a causal signal. We are going to use the unilateral Laplace transform to analyze this system. The h of t is e minus t ut. Again, it's a causal system. In fact, almost all our questions are causal system unless otherwise stated. The yt is equals to x of t convolved with h of t in the time domain. And now we want to analyze this equation in the Laplace domain to get the output. This is the Laplace of the cosine 1t multiplied by ut. This is the Laplace transform of e minus t. Convolution becomes multiplication, so we are finding the product of these two polynomials multiplied with each other, rational functions. I perform this multiplication using this function called convolve for the denominator. What about the numerator? The numerator is s and the denominator is s squared plus 1 squared s plus 1. So this operation below here is performed using convolution. 101 represent s squared plus 0s plus 1. So this is 101. What about this guy? 11 is s plus 1. So the coefficients are 1, 1. Since they are multiplying, we are using convolution to generate the coefficients. So hence we use convolution here. What about this guy? 10, 10 is representing this, which is the numerator. Only s, because this is s plus 0. The coefficients are 1, 0. Now, what am I doing here in residual? I am sending the numerator s and the denominator s into the residual function, and out comes rpk, 3 vectors. These 3 vectors, the answers are here. Let's try to remember what rpk is in MATLAB. Rpk will give the coefficient. This is called r1, this is called r2, this is called r3. This is p1, this is p2, this is p3. To use rpk, it is simply r1 divided by s minus p1 plus r2 over s minus p2 plus r3 over s minus p3. So this is r1 over s minus, this is p1. This is r2 over s minus p2. This is r3 over s minus p3. You can now simplify. So minus 0.5 remains on top. Minus 1 becomes plus 1. And here we'll join the terms together. And on top, we are cross multiplying. And again, we simplify. So this is ys on the right hand side. So you have to learn how to do partial fractions by yourself. Now, once we have this, in this form, there is a lookup table. In fact, we'll reach here, and the lookup table for ys in the time domain of this guy is simply minus half, which is the coefficients here, times exponential minus 1t. What about this guy? Well, we can simplify to this. The half goes out, and we have two terms here. Each one of them appears in the lookup table. This is the cosine, and this is the sine. So now we have the solution yt as this form. Remember I told you that if you send a cosine into a system, an LTI system, out will come a cosine of the same omega. That means the same frequency. What will change is the amplitude and the phase. But what came out, okay, is three terms. One term here, one term here, and one term here. I should put ut here. So how do we reconcile that? Well, the first thing to answer is this guy is a transient. When t is equals to 0, his value is minus half. But when t goes to infinity, this guy disappears. So he's a transient. What about this guy? A cosine adding with a sine of the same frequency actually can be represented as a cosine of that frequency with the amplitude and a phase shift. Now, if you forget how to do this, I'll suggest you to see Math Center, this website. Let me pull it out. Okay, Google this page, Math Center, with this term, and you will see that in this tutorial, he teaches you how to use or how to represent a cos x plus b sin x into a value r, capital R, cosine x, where x is this x, minus alpha, where alpha is a phase shift. So how do you do that? The expression came from this sum of angle rule. So r cos x minus alpha equals to r cos x cos alpha plus sine x sine alpha. And then you can simplify this to get what is capital R as well as what is alpha. Okay, so please take a look. So in summary, in this slide, what we did was we take a cosine of unit step and send it to the LTI system. Now, there's a few things that you need to take note. The LTI system is relaxed. There is no initial condition in this question. There's no initial condition. The output have two parts. That's the other thing to take note. It is a cosine that has the same frequency as the input, but now has a magnitude that is changed and a phase shift. So this is called the steady state response, because this cosine will last as long as the input lasts. What is interesting is that a transient came out. This transient only lasts for a few seconds. After maybe 5 seconds or 4 seconds, this transient disappears. This transient is due to the inertia experienced by the cosine. As the cosine is being pushed into the system slowly builds up, and after about, in this case, 4 seconds later, the inertia disappears. Now let us plot this solution. In the next page, we solved exactly the same thing using MATLAB. So let us see how we do. Let's see the figure first. The blue is the input, this green here is the transient. Its equation is minus half e minus 1t. Notice that it starts at minus 0.5 at time 0. And as time increases, then the exponential becomes smaller and smaller, and then after about 4 seconds later, it becomes almost 0. What about the steady state? We saw that the steady state is this equation here. 0.707, the amplitude is 0.707 with a phase shift of minus 0.7854. I worked this out. This is about minus 45 degrees. So we have the cosine that is with amplitude 0.7071 and a phase shift between here and here is a delay of minus 45 degrees. So the green bubble here shows the steady state. Remember that it is the steady state plus the transient, and it will give you the complete solution, which is the red guy. And you'll see that the red is moving like this, and at this point it's almost the same as the green, means that the red guy has already reached steady state. And what it does is that it keeps on going forever as long as the input is driving it. Now, if you remember the word steady state, the steady state can also be produced using the frequency response equation. What is the frequency response? It is nothing but setting S equals to j omega. So what is h of s? H of s is the Laplace transform of the impulse response. It is simply 1 over s plus 1. Now we substitute s equals to j omega. What is the omega we are interested in? It is 1 because we submitted 1t. So omega is 1 radian per second. Right? We push j omega with the corresponding value of 1 into the equation. Out comes 1 over j1 plus 1. Now we have this value. So this is a complex number. What is this? A complex number is changed into the polar representation, which is 0.7071 angle minus 0.7854. So it is nothing but with an amplitude of 0.71, angle of minus 45 degrees. Again, we don't like to represent things in degree. We prefer it to be in radian. Now, we see that if we use the frequency response equation with the corresponding omega, we can find the steady state amplitude and its phase shift immediately to produce the green guy over here. This green circle is the steady state response. Okay, we're now ready to see how we do this in MATLAB. What do we do? Set it to be symbolic s and t first with the correct parameter omega equals to 1. And what we are doing is first let me define e minus 1t to be the impulse response ht. To get h of s, we simply Laplace transform h of t. We want to find the Laplace transform of x of t, so we define x of t first, which is cosine 1t. The theta is 0. And we perform Laplace transform. To get the output is simply the input xs multiplied by h of s, and to get yt is simply the inverse Laplace transform of ys. So it's trivial. In MATLAB, it's only like 6 lines of code. The rest is to plot. Take a look at how I plot, and then the figure comes out. Okay. So the MATLAB is there to help you check your solution. Thank you.